In the previous lectures, we have defined the notion of metric spaces and considered plenty of examples of metric spaces. But our course is called functional analysis, so let's make a step to the analysis in these metric spaces. Today we will consider several special sets in metric spaces, and we will start with the notions of closed and open sets. We will need several definitions before we proceed. They are fairly simple. We define an open and closed balls in a metric space. An open ball we will write B X R, where X stands for the center of the ball and R stands for the radius of the ball. It is a collection of all elements from our metric space such that the distance between X and Y are strictly less than R. So this definition is fairly similar to what we've seen in calculus. And in a similar fashion, we will define a closed ball. We will write a square brackets for grid. It will be a collection of all elements such that the distance from X to Y is less than or equal to R. Sometimes we will call both of these sets neighborhoods of the point X, but in most situations when we will speak about neighborhoods, we will mean the open ball. Okay, now let's define the notion of a contact point. A point A from a set A is said to be a contact point of A if any ball centered at A and any radius contains a point from A. It is easy to see from this definition that any point of this set is a contact point. Because when we consider a ball of this form, it contains at least the center of itself, the point A, which belongs to A. But there are contact points of a set which do not belong to the set. This simple example will show this. So, the set of contact points of an open interval, we are on the real line with the usual metric, is the closed interval. Well, it is easy to see that any ball centered at 0 contains some points of the set A, and the same for 1. Using this definition of contact points, we are we will define the notion of a closure of a set. A closure. We will denote it by a bar of a set A from some metric space is a collection of all its contact points. Well, as we can see from this example, the closure of an open interval is the closed interval, which shouldn't be a surprise. Let me state several simple properties of the closure of the set. First of all, for every set in a metric space we have, first of all, the set cannot be larger than the closure of the set, which is fairly clear. If we take the closure twice, then we will get exactly the same result as taking closure once. Also, if one set is a subset of another set, then the same is true for their closures. And one more. If we take two sets, take the union and take a closure, then what we will get is nothing but the union of closures. So these properties are fairly simple, and I'm leaving them for you as an exercise. Let us briefly discuss a few examples of closed sets. We already know that a closed interval on the real line is a closed set. A closed ball in any metric space is closed. And also, it is easy to see that the set itself and an empty set are closed as well in any metric space. In any metric space. Now let me state and prove two very important properties of closed sets. This property tells us that an intersection of arbitrary and a union of finitely many closed sets are closed. So if we take arbitrarily many closed sets and take the intersection of all of them, the result will be a closed set. And if we take a finitely many closed sets and take the union, we will get a closed set. Let's prove. For the first part, let F alpha be closed sets and let F be the intersection of all of them. All F alpha. We take the intersection of all alpha. And let X be a contact point of F. What does this mean? By definition, it means that any ball centered at X intersect F. For every epsilon greater than 0, ball of the radius epsilon intersect F. But since F is an intersection of all Fi's, this means that this ball intersects any of the set Fi. For every I. Again, by the definition of a contact point, this means that X is a contact point of every set Fi. So X is a contact point of any F alpha. By the definition of the closure, we conclude that X belongs to the closure of F alpha. But all the sets F alpha are closed. So X belongs to every F alpha. And hence, it belongs to the intersection. So we have proved that F contains all its contact points, which means that F is closed. Let's now prove the second part. Similarly, let Fi I from 1 to n, so we take finitely many closed sets. Let these sets be closed. And let F be the union of all of them. For this part of the proof, we will take a point X which does not belong to F. And then we will show that this point is not a contact point of F. So if X does not belong to F, then X does not belong to the union of all of these sets. So F does not belong to any Fi. But we know that all Fi's are closed. Since all of these sets are closed, the fact that X does not belong to this set means that it does not belong to the closure of this set. So then, X is not a contact point. Of Fi for every I. Which means, by the definition of contact point, that there exists epsilon I such that ball centered at X radius epsilon I does not intersect Fi. Now, I will take epsilon to be the minimum of all epsilon I. By this construction, we have that a ball centered at X, radius epsilon, does not intersect Fi for any I, which means that it does not intersect X, which means that it does not intersect F. So we have found a ball centered at X such that it does not contain points from F, which means that X is not a contact point. And so F is closed. There is a simple property which restates the notion of closure in terms of convergent sequences. A point X belongs to a closure of this set if and only if there exists a sequence Xn of points from A such that this sequence converges to X. Of course, when I say that this sequence converges, I mean that the distance between Xn and X tends to 0 as n tends to infinity. Now let's go to the notion of an open set. Again, we will need some auxiliary definition. A point from the set, a point X from the set A is said to be an interior point of A if there exists some ball centered at X which lies inside this set A. Such that ball centered at X and radius epsilon belongs to A. And a set is said to be open if it consists of interior points only. If all of the points of A are interior. Well, as a simple example, an open interval in the real line is an open set. An open ball is an open set. There is a relation between open and closed sets, and we will discuss this relation in the following theorem. A set A in a metric space is open if and only if its complement in X is closed. So the set is open if and only if its complement is closed. Let's prove it. First, let A in X be open, which means that every point of A is interior point. So it sits in A together with some neighborhood. And let A be a point from A. So there exists epsilon say 0 such that a ball centered at A and of radius epsilon 0 belongs to the set A. But this means that this ball, if we intersect it with the complement of A, then the intersection will be empty. So, we have found a ball which does not intersect this set. This means that the point A is not a contact point of this set. So, we've taken an arbitrary point from A, which means that it does not belong to this set, and showed that it's not a contact point. This means that the set X minus A contains all its contact points. Which means that this set is closed. The proof of converse station is pretty much the repetition of this argument but read backwards. Let's go through it. Let A from X be such that A set minus X set minus A is closed. Hence, this set contains all its contact points. In other words, any point outside of this set is not a contact point. Hence, for every point X which does not belong to x minus a, but this means that x belongs to a, there exists epsilon, say 0 greater than 0, such that the ball centered at this point x does not intersect this set. But this means that this ball lies entirely in the set A. And so x is interior point of A. So we've taken an arbitrary point from A and showed that it's interior. So all points of A are interior, and so A is open. We have discussed already that in any metric space, this space itself and an empty set are closed sets. But we know that an empty set is a complement of X in itself. Using this theorem, we conclude that the set X and an empty set are open as well. So they are closed and they are open at the same time. Sometimes these sets are called closed sets. But this is the feature which we already had on the real line. So the real line itself and an empty set on the real line are open and closed at the same time. But can we get some more here? Can, for instance, an interval be a closed set? Let's consider another example. Let our set be the union of two intervals. And on the real line, and the metric will be the usual metric on the real line. Then, what can we say about the set 0, 1? It is open. And the same for the interval 2, 3. They are open. But on the other hand, the interval 0, 1 is a complement of 2, 3 in X. And the same is true for 2, 3, which is a complement of 0, 1 in X. So they are closed as well. So they are closed. Let us now speak about counting, or rather the way how we count. When, for instance, we want to count the number of desks in this class, how do we do this? We point at the first table and say 1. Then we point at the other table and say 2, then 3, 4, keep pointing and keep pronouncing the natural numbers. That's how we always count. But in fact, by doing so, we describe a function which provides a correspondence between the objects we're counting and some subset of natural numbers. Let us speak about this more formally. So we need a couple of definitions. So, let's take a function. In the metric spaces world, they are typically called mappings or map. A mapping phi from set x to set y is one to one, or it is also called a bijection. If for every element from x there exists a unique element from y such that phi of x is y, and conversely, for every element from y there is a unique element from x with the same property. This is exactly what we did when we counted. When we counted desks, we count all of the desks, and to each of the desks we attach a natural number. And that was only one number attached to a single desk. And none of the numbers were attached to two. And none of the numbers left. Speaking of, when we call a one-to-one map a bijection, it means that that's an equivalent definition. Equivalently, by bijection, it means that this mapping is injective. That is, if x1 distinct from x2, then so are the values of phi. And it is surjective, which means that phi of x is the whole y. Or in other words, that this mapping is onto. This notion of one-to-one mapping, we can define equivalent sets. So that's another definition. Two sets, x and y, are equivalent if there exists a bijection. From x to y, if there exists a bijection. So if we have two sets and we've managed to construct a bijection between two of them, we can, roughly speaking, say that this set has the same number of elements, although the number of elements in each of them can be infinite. That will be another definition. So probably the simplest set which contains infinitely many objects is the set of natural numbers. And we will call any set equivalent to natural numbers countable. Well, this term actually suggests what we can do with these sets equivalent to natural numbers. We are able to count them. it doesn't mean that we can count all of them, because it will be infinitely many of them. But this means that we do have ability to count them. So we know the algorithm of counting. Let us also introduce a name for the sets which are not countable. It's not a surprise that they are called uncountable. Let's consider several examples of countable sets. The first example is the set of all even numbers. Although it might look like there are twice as many natural numbers than there are even numbers, but in fact they are equivalent. And to prove that they are equivalent, we need to construct a bijection from the set n to the set 2n. And it's not very difficult. This bijection will be f of n equals to 2n. It is fairly straightforward to verify that it is in fact a bijection. Another example is the set of all integers. The set of integers is also equivalent to the set of natural numbers. I leave it for you as an exercise to figure out what kind of bijection can prove this. Even more complicated example is the set of all rational numbers. That is, all the numbers of the form p over q, where p is an integer and q is a natural number. To prove that the set of rational numbers is equivalent to natural numbers, which means that the set of rational numbers is countable, we will present an algorithm for counting. So since we have two parameters, let me write down a table. Over here, I will write down the natural numbers. And vertically, I will write down all the integers. From 2, we know that the set of integers is countable, which means that it can be written as a sequence. We do not care much about each particular value of elements in this sequence. We just want to know that it can be written as a sequence. So let me write it as A1, A2, A3, A4, and so on. And by construction, in this table, we will have all the rational numbers. Let me call them A11, A12, and so on. And now I will draw an algorithm for counting. I will start with A11 and go down to A21. From A21, I will go diagonally to A12, then to A13, then back diagonally, and then down. That's the algorithm for counting all the rational numbers. And this proves that the set of all rational numbers is countable. There is one more interesting example which will be an exercise for you. So the set of all polynomials with rational coefficients. The set of all polynomials with rational coefficients is countable as well. In this lecture, we are mostly interested in the countable sets. Anyway, let's briefly mention one uncountable set and prove that it is uncountable. That will be the interval 0, 1. Proof. First of all, let's note that any number from this interval can be written as a fraction, decimal fraction. Can be written as 0.x1, x2, x3, x4, and so on, where all xi's are numbers from 0 to 9. Well, it is clear that x can be written in this form, say all xi's are zeros, and 1 also can be written in this form when all xi's are 9s. But we should be careful because there are some numbers from this interval which have exactly 2 representations of this form. Say half can be written as 5 and then all zeros, and also it can be written as 0, 4, 9 and then all 9s. We should be careful about this. In our construction we will avoid this case to avoid miscounting. Okay, so to prove this we will suppose to the contrary. That is, the set 0, 1 is countable. But this means that all elements of this set can be written as a sequence. So let's do this. Say A1, A2, A3, A4, and so on. But all of these numbers are elements of 0, 1, so they have a decimal representation. So for all of them we can write A11, A12, A13, and so on. And for this one, similarly. And by doing this for all of these numbers in this sequence, we have a decimal representation for each element of the interval 0, 1. And now I will construct a number from 0, 1 which is not in this list. So I'll take Bn to be 1 if A and N is not 1, and 2 if A and N is 1. So I specifically choose the values 1 and 2 to avoid zeros and nines, so to avoid miscounting. And I will set B to be a decimal expansion. As we can see, the first decimal place in B is distinct from A11 by construction. So B does not equal to A1. The second position, B2, is not the same as A22. So B does not equal to A2. Similarly for A3, A4, and so on. With B constructed like this, we conclude that B does not equal to any of the AIs from that list. So what we managed to prove? Initially, we assumed that this set is countable, and so all its elements can be listed as a sequence, all of them. And then we constructed an element, let me state that it is from 0, 1. An element of this set which is not in that list, which contradicts our assumption. The last thing for today is the notion of separable spaces. Separable spaces. Again, before defining the separable spaces, we will define some additional auxiliary terms. If we have two sets, then a set A is said to be dense in B if B belongs to the closure of A. And now we can give a definition of a separable space. So a metric space is said to be separable if X contains a countable dense subset. So if in our metric space we can find a countable subset such that the closure of this subset coincides with the whole space, then this space is called separable. Examples. Most of the metric spaces which we considered before are separable. Let me mention a few of them. well, R1 with the usual metric is separable because the rational numbers are dense in R1. So the set of rational numbers is countable, and the closure of them is the whole R1. The same story for Rn. I will write over here P, showing that it's with P metric. For every P from 1 to infinity, including infinity. These spaces are separable, and the countable dense subset is constructed based on rational numbers. Another example is the space of continuous functions on the interval AB with the uniform norm with rho infinity. So this space is also separable, and the countable dense subset in this one is the set of all polynomials with rational coefficients. Well, let us finish with the example of a non-separable space. Theorem. The space L infinity of bounded sequences with the uniform norm with rho infinity the space of bounded sequences with rho infinity metric with the uniform metric is not separable. So to prove this, we will construct an uncountable subset of L infinity such that the distance between any two elements of this set is half, or even 1. Proof. Let A be a subset of L infinity such that all coordinates of x is either 0 or 1. So it is a subset of all dyadic sequences. Let us first know that if x and y are dyadic sequences and they do not equal to each other, then the distance between x and y, which is by definition supremum of xi's minus yi's for all y in natural numbers, then this supremum equals to 1. So we have the whole set of sequences such that the distance between any two of them, any two distinct sequences from A, is 1. Now let us show that this set A is uncountable. First of all, let us construct a function. Consider a function from A to the interval 0, 1, which is defined like this. So the value of this mapping on a sequence X will be we will take the coordinates of x and multiply them by 2 to the power of minus I. So this expression, in fact, belongs to 0, 1. We should be careful about this mapping. It's not a bijection. Indeed, if we take phi of a sequence where only the first component is 1 and all the others are zeros, then the value will be half. But also, if we take this sequence where the first component is 0 and all the rest of them are 1s, then we will get this sum, which is 1/2 as well. But this only happens if this number x from 0, 1 is dyadic rational. That is of the form p over 2 to the power of q. But the set of these numbers is countable, as you can easily prove. So, if we remove these numbers from the set 0, 1, then we will get that the mapping phi is a bijection, which means that the set A is uncountable. So we managed to construct an uncountably many sequences from L infinity such that the distance between any two of them is 1. What I will do now is I will consider a ball of the radius half around any of these points. For every element x alpha from A. Since the distance between any two elements is 1, we conclude that these balls do not intersect each other. So, what we've done is we constructed a collection of balls which do not intersect each other, and this collection is uncountable. It is uncountable. So, if there exists a countable dense in L infinity subset, any, or rather just dense, so any subset which is dense in L infinity should contain at least one point from any of these balls. So this set must contain an uncountably many points. This means that L infinity is not separable.